Hello calculus people. Today I want to talk about the first derivative and the second derivative and how we use it to determine when a function is increasing or decreasing, and how we can use the second derivative to determine where the function is concave up and concave down. First thing we want to do is let's do a little graphing to understand through drawing sketches what the shapes of these types of increasing and decreasing behavior or concave up and concave down behavior can look like. So in the first task I have us looking at is let's draw a function that is increasing and concave up. I'm going to pause so that you can draw it, and then let's see if your graph matches my graph. Okay, so now I'm going to come back and I'm going to draw a function that is increasing. So from left to right, the function is increasing, and it's going to have upward concavity. That means that when you look at it, it has a upward facing curvature. So in the next one, we want to draw a function that is increasing but concave down. So you can pause the video here to see if you can draw it, and then check in after you try drawing your function. And I'm back, and here's the function where the function has increased from point A to point B, but as it increased, it had what we would call downward concavity or downward curvature. Just for your information, a line or a curve that has no curvature, I guess that's a contradiction, but a function that has no curvature is a straight line. So for example, y equals x plus 3. If you were to analyze that curve or that function, you would see that that has no curvature. Let's look at, I'm going to put the next two up, and I'd like you to try those. Try to draw your function that's decreasing and concave up and decreasing and concave down, and see if you can match what function I draw. Okay, and here we have it. We have a function that has definitely decreased, but it's maintained its upward concavity. And I usually will say to people in class that we have upward concavity and we have downward concavity, and I always try to remind people that concave down makes a frown. And sometimes that riddle helps people, but usually people will recognize after drawing it once or twice what downward concavity is. Some people may draw a function where it increases and has both upward and downward concavity over an interval. So let me try drawing that. So it will increase with upward concavity, and then it will transition to increasing with downward concavity. And at this point here, we call that an inflection point. And that's a point where the concavity changes. So in order to find an inflection point, you have to find where the concavity would change from either upward to downward or downward to upward. Now, what I'd like you to do is I'm going to zoom out, and I'd like you to match up the language of increasing at an increasing rate and increasing at a decreasing rate, and decreasing at a decreasing rate and decreasing at an increasing rate to the graphs that we just drew. So I'm going to match them up with the numbers, and then we'll discuss that after you have a chance to do that on your own. Okay, so we're back, and we're going to first do increasing at an increasing rate. Well, a function that increases at an increasing rate is one that has a positive first derivative and a positive second derivative, and that would be one that looks like this one here, where the derivative was greater than 0 and the second derivative is greater than 0. So this would be choice 1. Increasing at a decreasing rate would be one that has a positive first derivative and it has a negative second derivative, and that's why the second part of it, the concave down part, we say at a decreasing rate. It increases at a decreasing rate. The next one, it decreases at an increasing rate. Now this is one that, well, let me make sure I get that correct. I want to put 4 here. It decreases at an increasing rate, and if you look at it, it's got a first derivative that is less than 0, but its second derivative is greater than 0. Its concavity is positive. Now, people may argue with me on that point, but I can prove that to you. But the last one would be number 3, where it decreases at a decreasing rate, and this, you can see here that the first derivative is definitely negative, and the second derivative is also negative because of the curvature you see. So, looking at the third function, or the third graph, the way you can think about why is this decreasing at an increasing rate, I'm going to use a different color here to mark out the slope lines. So we know the first derivative represents the slope. So you would say the slope here is maybe -2, the slope here is maybe -1, and the slope here is, it's not 0, but let's say maybe it's -1/2. Since we have slopes going from -2 to -1 to -1/2, let's put them in order. -2 would be the lowest, -1 would be the second lowest, and -1/2 would be the greatest value. And clearly you could see that the slope values are increasing. If the derivative is increasing, then that indicates that the second derivative has got to be positive. Hence, the function is decreasing at an increasing rate. Now I'd like to turn our attention to using this information to helping us find out where a function may have a local min or max, using the first derivative test, then talking about how we use the second derivative to find out where a function is concave up and concave down through using algebra, and then we're going to verify it with a graphing calculator. What I'd like you first to do is take the first derivative for this first part and find the critical points. I've taken the derivative, I factored out a 3, I then factored the x squared minus 9, and I have two critical points at x equals -3 and at x equals 3. The next part is to draw a number line to do interval testing. And I know that the derivative value is 0. If I take a test point and I plug it into the derivative equation, which is fully factored, so over here I'm going to take advantage of this equation, and I'm going to plug in my test point into that derivative equation, I'll be able to tell using a sign test if it's positive or if the derivative is positive or negative. So I'll plug in -4, and when I plug in -4, my derivative is going to be, for the first part, when I plug -4 and I have a positive, a negative, and a negative, and that would make the derivative positive in that portion. When I plug in a number in between -3 and 3, let's just say we use a value 0, I'm going to get, my sign will be positive for the 3. For plugging in 0 into x plus 3, I'll get a positive, and for x minus 3 I'll get a negative, so I'll have a negative overall sign when I multiply those signs. And then I'll try the point outside, which is 4, and when I do the same sort of thing, I'll end up getting a positive. This indicates that in this interval my function is increasing, in this interval it's decreasing, in this interval it's increasing. So you would write down your statement as far as the function and it increasing or decreasing. F of x, or I'm sorry, the question is for a local min or local max. F of x has a local min at x equals 3 because f prime of x changes from negative to positive, and that means the derivative is telling you the function went from decreasing to increasing, which indicates a local min. You write up the statement for f of x having a local max on what intervals that, not what intervals, at what points that happens, and we'll compare answers. Okay, we're back. And hopefully you wrote down f of x has a local max at x equals -3 because the derivative changes from positive to negative at that point. Now let's use the second derivative to tell us what this function is doing. We take we start off with this function again. We have f prime of x we start off with is 3x squared minus 27. We take the second derivative, which just is going to be 6x, and when we set that equal to 0, this is a very easy equation to solve, obviously. At x equals 0, we have what's called a hypercritical point, or you could call that a possible point of inflection. At this point, this is if we can show if the concavity changes, then we know for sure it's a point of inflection. I'm going to just do a number line test. Again, I make my second derivative number line. This is going to be pretty easy to do on this case because we just have 1 point at x equals 0. So when we interval test 6x, when we have a negative number, we have negative concavity, and when we have a positive number to plug in, we would have positive concavity. So that would indicate that on this interval we're concave down, and on this interval we're concave up. So let's put together the whole picture. If we were to draw the whole picture, or let's just verify it with our graphing calculator and identify those regions. Okay, everybody, so I graphed it on the graphing calculator, and we're looking at a picture of it, and this is the function y equals x cubed minus 27 x minus 5, and notice I had to use these window settings so I could make the graph fit. But you should notice that at 0 we have a point of inflection that connects a concave down region with a concave up region, and we also have we said that at 3 and -3 we would have our -3 we have our relative max, and at x equals 3 we have our relative min. So hopefully this video was of help to you guys in understanding how to use the first and second derivative to come up with intervals for increasing and decreasing, and local mins and local maxes, and the intervals for where a function can be concave up or concave down.